Okay, so I think that it's recording what I'm saying and what I'm writing, and it'll be up there on YouTube. I've tried it without a headset, and every now and then it gets like really scratchy and loud. I wonder if I'm not like handling it. So we'll see how that works. I don't feel comfortable doing that for class, but for the exam review, where it's just kind of loosey-goosey answering questions and that sort of thing, I don't mind doing that. What I was saying was that if you've got your characteristic equation and you need the roots, you can just get the roots and then come here, and this will tell you if it's decaying or oscillating. Okay. If you don't need the roots, but you still need to know what this is, don't solve for the roots. That's just extra work. Okay, but just put the characteristic equation in this form where you've got a 1 coefficient here for this s squared, and then look at your a's and b's and compare, and that will tell you what's happening there. Okay, so that was a special way that we used this table. Now, there's a table that we didn't use at all. Well, I'll say we haven't used very much since the last exam, and that was this. Okay, this was a kind of a special thing for zero initial conditions. We liked that because we didn't have to go through the solution method down here where we just put in this form and then we need to use the initial conditions to solve for these coefficients. Okay, and so this doesn't have a solving for coefficients, so this is nice. But this form over here, it's a little bit clunky. There's kind of specific situations where this works. And so you can, I don't think I'm going to even include this on the exam formula sheet. Okay, and I'll make sure to not have anything that would require that. These zero initial conditions, we can do that with the transfer functions now, and it's actually it's easier. It's easier than this when we use the transfer functions. You know what? Is it worth? No, I was going to show you. I was going to work an example and just do this, but without having to say what's my A, what's my B, and that sort of thing. But I won't. I won't do that. I'm careful just because now that you've got the homework solutions, there's a lot of deep explanation in there that you'll see. So yeah, I'll just say this. So you don't need to. You can forget about this for the exam. Okay. Now, a significant thing that we did is we talked about time constants. I mean, we did that just a little bit last time, but there's a lot of instances here. If you look back at the homework 3 and homework 4, where it says, how long does it take to stabilize? Does it decay? If so, how long does it take? And it goes back to this 4 time constants. It comes to this statement right here. Right here. At t equals 4 tau. Okay, and that we say that means it's 98% of the way there. So we'll say that that's arrived. And so this, let's see, I'm starting to lag all of a sudden. Oh, maybe because I'm doing this internet thing. Hang on, I think I missed it. No. Aha, there we are. So this is important. So we now actually know how to use this, right? For the first exam, we said, well, MCK, I don't know, it's just a thing, right? And we were just doing it that way. And it was a little bit frustrating during the first exam when we had kind of these two sets, right? That we had this second order equation with 1, A, and B as these coefficients, and then C over here. And then we also had to play around with this where we had M, C, and K. And so M is 1, A is C, and K is B. And so we'd have to kind of go back and forth and wonder about that. But now that we know that this is our, right here, that this is our damping coefficient. So this was in chapter 4, right? That we just started to use the damping, and then we would end up with equations like this, and then we would be able to calculate that. You'll see it on the homework, but I will just emphasize, just because we did it a lot in class the other way, is that this only works if your damping constant is less than or equal to 1. Okay, that is going to be your time constant. If your damping ratio is more than 1, then you have to just look at your final equation and look at the exponential in that way. Okay, and so this is going to be significant. You know, this is very, very heavily useful for the spring damper stuff in chapter 4, and then kind of as we go on, everything's going to turn into springs and dampers, right? We talked some about how structures, right, or springs. You know, the lubricants, that would be a damper. You know, and as we go on, we'll talk about fluids. We'll talk about electrical systems, electromechanical systems, thermal systems, and you'll see kind of the spring effect and the damper effect in all of those things. And so this is going to be, for this exam and on, this is going to be a very useful form.
How do you tell if it's conservative based on the chart? And would you use either the natural or the damping ratio?
Easier. If C is not equal to 0, not conservative. Okay. Well, if there's no friction. Okay, so it's damping and friction. Don't think about friction. I'm not gonna surprise you with friction on this exam. Okay, so you can forget friction. So without thinking about friction, if there's no damping, then it's conservative. Okay, but damping can be anything. It can be wind resistance, like that baseball problem from one of the first homeworks that we did, or it can be kind of what we've been talking about, the lubrication and that sort of stuff, and the bearings and that sort of stuff. That makes it conservative or not. Okay, so that's pretty straightforward. And you see, of course, if C is 0, then damping ratio is 0, meaning it's not being damped, which means the damped natural frequency is just the natural frequency. So you don't need to go through all of that. It's just going to be no damping, no, that it is conservative. And so look at this also, you know, kind of in that same kind of higher view of damping. If there's no damping, there's no time constant, right? Or as this says, time constant is infinity. And that's because if there's no damping and it starts to move, it's never going to stop. Okay, it's always going to be oscillating. And so, yeah, there's not going to be a time constant. It's going to be infinite. It's never going to come to rest. Okay. So conservative or not, you can look for damping. Okay. And so when we did the energy methods, there in chapter 4. Okay. Do you remember this where we said this? There we go. Where we said the kinetic energy, that's really Ke, that's the kinetic energy. This is this mgh, our potential energy, and then this was our 1/2 kx squared. And so that's for the spring potential energy, right? So we have the spring potential energy, and we've got the gravitational potential energy, and then the kinetic energy, and we say that's constant. And so you can say, and I'll just say this here. System won't have dampers. Okay, or friction. Okay. That makes it conservative. Okay. There's some introductory material. Also in chapter 2, there's some introductory material on the transfer functions here in chapter 2, although we didn't go into great detail until just recently, right, with the transfer functions. We find that the transfer functions are particularly useful when we've got first order equations, or we've got multiple equations that are that are linked. Okay, so you'll find transfer function things here. You'll also find some stuff that we did with the impulse. But I would say just refer to your notes for that rather than coming back here to chapter 2. However, if you want to practice some of those problems, you know, there's a lot of good practice stuff here in chapter 2. You know, there's some transfer function practice here. There's some impulse. Well, impulse. I like the impulse. You'll see that I've used it a couple times in the homework. This idea of the 0 minus and the 0 plus, we haven't really developed that fully. So I would say don't worry so much about the 0 minus and 0 plus. Okay. The important business about the impulse function that you're going to need to know, you'll pretty much be able to solve from right here. And that is just that if your force is an impulse, then your capital F is going to be 1. Right? Same thing with the unit step. There's a fancy way to derive all of that. You know, all we're saying here is that if this is your F of t, then your F is 1. Here we're saying if your F of t is US of t, then F is 1 over S. And that's what you'll plug in, and you'll kind of go through. So that's the extent that we use the impulse here on the exams. Okay, so there's going to be some interesting things there, and that's the scope of what you're going to need to know from chapter 2. You know, we did a little bit a long time ago about you put in the exponential e to the negative st, and then you do some integration. We're not going to do any of that, but it's really just kind of the higher level stuff, and we're going to use these tables here as the tools for what we've done since then. Okay. Now, chapter 3 is very much specific to kind of unique so there's a lot of interesting configurations, right, that we have here. Things moving, let's see, translational motion. So we talked about some friction here. We can ignore the friction. So this inertia business is going to be important. Okay. So you've got the inertia. So you've got this table. And I'll just put this here. And I'll show you kind of how we can work these. You've got the table 3.2.1. And we kind of compare that alongside this other table. Let's see, did that not? Here in chapter 4. Right, so you remember there's two. There's this little bit here for the torsion. Here. Kind of put these side to side. Oh, I can't zoom in very well. I'll just do it like this. Okay. So we're going to use these together, right? So in the first exam, we did some things with this moment of inertia where we had to calculate it and use it. And then we now used some similar shapes, and now we've got the spring constants here. You know, I can think of, for example, that diving board example. You know why I made that diving board example or the homework problem is because I was sitting, I said, I wonder, could you really make a diving board out of particle board? And I didn't know. And so I said, I'm going to make it a homework problem. And so I killed two birds with one stone. I figured out that you could not, unless it was really thick. Well, of course, you wouldn't want to get it wet either. Unless you put like that truck bed liner on it, but then that'd be really redneck. We don't have a pool anyways. But remember, we had to use both. That it was the bending and this stuff for the fixed beam. There was a little bit that we did also where we kind of developed these formulas just using the I instead of this. And so I'm going to I'll include that formula. But not the dimensions. Do you remember there was an example that we worked. Well, I'll just give me on one. There's an example that we worked where we didn't know the K, but then we did know the I and some of the other properties, the Young's modulus, and we were able to do that. So I'll provide that form or that formula for you if that's going to be something that's going to be on the exam. So you just keep that in mind that there is going to be an alternative also if you don't have these specific dimensions. But if you do have more kind of real world things where you've got a known moment of inertia, but you don't have those dimensions exactly. Okay. Okay, so if you remember, chapter 3 was a lot of movement in a lot of different directions, right? So we had some combinations of things, right? We had rotation and translational motion kind of combined, and we were doing those types of things. We didn't see that so much in chapter 4, right? It was a little bit more basic as far as the movement. Now, we did have translation, and we did have rotation. I don't recall, I don't think we had to do the effective, did we do effective mass or effective moments? But in chapter 4. We didn't have to when we would solve these types of problems. Because, you know, even when you have something like this.
What about the figure below that, the 416? Did we have a problem where we had to take into effect?
Yes, but it was not a combined. So yeah, so it was not this. Okay, where you had this effective, where you had this either the effective mass or the effective inertia, and then you had to solve it that way. That was one of the areas where I noticed a lot of confusion also on the first exam, and I think there's ways that we can get around it. So I think if I'm careful, I don't know. Now'd be the best time though to ask you another question using effective mass and effective inertia. You know what? Nah. So if you see a problem that you on the exam that you think you need to use find some effective mass or effective inertia, think again. Okay, and I'll make sure there's not any questions that require you to solve it that way. Now that might be a possible solution method, but I'll make sure that if you don't know anything about effective mass, effective inertia, then you'll still be okay. What you'll find here in chapter 4 primarily is how do we handle springs. It actually gave us these relationships for the springs, and then it talked about how do we handle the dampers. So there's not, excuse me. So there's not a table. You'll notice here there's not a table that says, oh, if you've got this shape, or if you got this object, it's this type of damper. If it's this or that, there's not going to be any formulas for the dampers. Okay, you'll have a C value. Okay, so what that C value is really is kind of a CFD question or an experimental. It's like fluid dynamics. You know, the baseball equation that we used, or the baseball example where we had some, here's the air resistance and it was some C. It's really not going to be a linear function like that. It's like the density times the velocity, some cross-sectional areas, velocity squared actually. And so those C's are complex. So if there's a C, you'll be given it. Okay, I mean, there's not going to be any equations for, you got to figure out what the C is based on some shape or anything like that. Okay, so the springs though, the springs, you have tables, okay? Dampers, no tables. Okay, we're calling them dampers. We've been doing dampers all along, ever since we started using terms. We started using second order differential equations with an A coefficient or a C coefficient right here. We've been doing dampers. So the solution methods, excuse me, should be familiar to you. Okay. A new thing is this energy method. If it springs, you can use it. If it springs and dampers, you can't, right? Because it's not conservative. And you saw some examples. There's some examples here how we go through it and do that. There's some homework examples. We also did some examples in class where you just find potential and kinetic energy at some place, and then we use this this formula here, just that the change is going to be 0. Well, okay. And so that's essentially the energy method, and you just find two states, calculate everything, and then you'll be able to do that. There was an example that I worked that keeps coming up in conversations where I did kind of this mass was falling and it hit this platform, and there were some different heights of springs. The solution method that I did there was kind of dumb. I mean, I picked the most awkward place for my 0, my x equals 0. And so I just did that so that you would know that you can put your origin and you can put your x direction anywhere you want, and that'll just affect, the answer will all come out the same. That'll just affect the complexity there. So I hope you didn't learn, oh yeah, I need to always put my x equals 0, some weird place. So by looking at some of these, the trick is identifying your states, identifying your 0 states for your potential energy. Okay, you know what 0 kinetic energy looks like. Okay, we did a little bit here with collision and impulse. This returns back to what was covered in chapter 2, and it goes into some greater detail here about how we would do this. This is where it really emphasizes the 0 plus and the 0 minus, and we did some things in class where we compared them. The way that they do these problems with the inelastic collision and the elastic collision are useful more than excuse me, more than impulse response. I would call this, or more than a impulse response section, I would more call this the impulse momentum section, or maybe the momentum section, or something like that. Okay, and that is just if it's purely elastic, then you've got a conservation of momentum. However, if you'll start here, and you've seen these equations. If you start here, you'll never really need to go back and use the conservation of momentum, because that's what this is. That's what this is. They've kind of derived these equations. Interestingly, they don't emphasize these equations or make them bold or put a box around them or anything like that. But this is essentially this conservation of momentum combined with conservation of energy. Okay, and so if it's purely elastic collisions. I don't know how to spell. Or perfectly elastic. I guess that's the word that they use here. Okay, and you've seen those. We've done examples of that. Something hits and it sticks. Something hits and it's perfectly elastic, and that'll be okay. These are good examples here. Inelastic and elastic collisions, but we've covered those. So you can expect something, not this 0 plus 0 minus stuff with collisions, but you can expect a little bit on collisions here for this exam as well. Okay. I am going to ask some Simulink questions. Just seeing who's paying attention. No, I'm not. 5.1 and 5.2. That's all we're doing here for chapter 5. There's chapter 5 is more block diagrams, but I've kind of rolled a lot of what's done in chapter 2 with the transfer functions in here because I think this is a good place to kind of package all these together. You know, I find chapter 2 more as like a instead of something to learn, it's more like a reference, right? You just go back to all the stuff that's there as you need it. And so that's kind of how we've been doing it with the impulse, with the transfer function stuff, which is introduced back in chapter 2, but we're using it really well up in here. Transfer functions, there's a little here, but this is enough. This is maybe more than in the chapter 2. This talks about how you're going to combine multiple. In this case, these are two first-order differential equations. You could also say that these are state variable equations. So if you just say x and y is the state variable, now you've got your two state equations, which is just the derivative equals whatever. And as long as there's no derivatives to the right-hand side, that's a state equation. Okay. Since these are two first orders, you're going to have two state equations, and your state variable here is going to be x and y. And so in chapter 5, and you'll see that I think a little bit in the homework, you go kind of back and forth between the state variable or the state equations, the state variable forms, and transfer functions and block functions. Right. So those are kind of three different ways to represent the same things, right? So your state variable form here. Maybe I'll write this down. This is going to be sets of first order equations, of first order ODEs. Okay. Transfer functions are going to be sets of, I'm going to change this to model. Sets of transfer functions make or define the system. Sets of first order ODEs define the system. Okay, and for the block diagrams, I'll say block diagram model. I don't know what you call it. I mean, what would you say? How would you describe that? So it's like interconnected operation blocks or something like that, but it's kind of a graphical. Maybe I'll do this. So I'll say dependence and operations. Okay, so I should be able to give you any system, and I would describe it. I would say we got this pulley and a spring and a mass, or we've got this, a bicycle riding down the road, and I would say, well, that would be first order. I would say put it in state variable, give me a state variable model, give me a transfer functions model, give me a block diagram model, and you should be able to do that just from a picture, just from a picture, right? And that would be kind of combining all the things that we do. You'd go in, you say, okay, what are my forces? What are my spring elements? What are my damper elements, if any, right? So think this. So spring elements equals spring elements. This is going to be something X. Okay. Damper elements is going to be something X dot. Okay. And Newton's second law is going to give us this X double dot. Okay. And maybe I'll say input. Oh, excuse me. There should be T's. Okay. So if there's a diagram and there's an arrow with an F, those are these inputs. Okay. We've done, so the ones that are stable are step functions, impulse functions. Okay. We've also done some shifted step functions, if you remember that. We actually have that here where it talks about a shift. Do you remember this? This unit where we say, okay, we've got a step function, but it doesn't start until a little bit later, or we've got a pulse that lasts for 5 seconds and then it stops. So we're not gonna worry too much about that, about doing these shifted step functions. Okay, and the reason is this shifting is only interesting if you also have some initial conditions, some non-zero initial conditions. Right, and so get something swinging, and then a little while later we'll apply this force or something like that. Okay, and so this has more to do with initial conditions. It was more interesting with the initial conditions, so we're not going to do that. Oh, where was I? Okay, so here we've got our double dot, dot, and no dot. Okay, and so combining all of these makes our differential equations. Okay. If there's dampers, it'll have this term. If there's springs, it will have this term. Sometimes they will have one or the other or both or neither. Okay, but this comes from Newton's second law. And so the way that we're going to develop these equations is always going to be through Newton's second law, right? And that would be okay. It would be something like that. If we wanted to do that for rotation, Okay, and so that's kind of in summary, that's the methods that we'll use is identifying these elements, then using Newton's second law to develop these differential equations, and then use the Laplace method usually. Well, I call these forms. This is all, we solved these from Laplace. So we would use, so these tables and the methods from chapter 2 to essentially solve the equations that we developed just from applying Newton's second law to whatever object we've got. Okay, so on the exam, expect to see stuff. Okay, and if it's stuff, that means you need to think of, okay, mass, spring constants, dampers, moments of inertia. Okay, and then from all that information, you yourselves will develop this equation that you'll solve. Okay. You know what? I'm doing a lot of gestures over here, but I guess you can't see that. Or there's not going to be stuff. Okay, if I give you equations, then you're not going to be thinking, oh, damper and mass and moments of inertia, because you'll already have the equation. Okay, and so either way, if I get you started by giving you just an equation with x's and y's and numbers in it, you'll know how to do it. Or if I give you stuff where you actually need to apply Newton's second law, dampers and springs and some kind of inputs, then you'll be able to do that. Okay. Did I answer your question, Michael? You asked a question that I think I wanted to really address. I feel like I've kind of covered that whole range of what from chapters 1, 2, and 3 can you forget and not focus on, which is all of chapter 1 and some of 2 and 3, and what of chapter 2 we're going to carry over, what of chapter 3 we're going to carry over, and also kind of the new things from chapter 4 and chapter 5. I am anxious so I don't have the exam. Well, I hadn't even started making the exam. Dude, I was up till 2 o'clock in the morning trying to get your homework solutions. Man, I've been working on that. I told you I'd give you the homeworks last Thursday, and it wasn't until, was it yesterday or day before, that you got the homework for? I don't know. That's been my number one priority. So once I have a general idea of the construction of the exam, I'll produce that formula sheet, and I'll get that out to you as soon as possible, just so that you'll be able to familiarize yourselves what part of which page, certain tables and formulas and stuff like that are on. Also, I hope to get it out to you in time so you can text me back with some complaints. Say, hey, Dr. Cruz, why don't you put these equations on there too? Or I noticed that you didn't really give these formulas, but I think we covered that enough in class. Is that something that's going to be on the exam? So that can be a little bit interactive and help you. So there may be things that you'd like me to add, and I'm fine adding. Sometimes I'll reply back and say, don't worry about it. You're not going to need to know that for the exam, which is also going to be a help for you as far as how to prepare. Okay. Can you think of any questions to pull out maybe some things that that you'll need to know for the exam that I didn't say? Okay. I'm around. Text me if you need me. However you want to reach me, don't throw bricks through my windows, and don't call my cell phone. But anything else than that, come by my office, text me. You can look at my windows, because I walk around in pajamas, not anything less. But don't throw rocks through my windows. All right, thank you very much. Good luck, everybody. Good luck. And I need to stop this video. And I'll go and post this for what